Hi, this is Tim Shu from San Jose State University, and I'm going to talk today about the trigonometric functions. After describing what they are, sort of, you'll see what I mean, we'll talk about the graphs a little bit and then get onto the other trig functions. Okay, so most of what I'm going to talk about right now is the definition of cosine and sine, except sort of, only sort of. And what do I mean by sort of? What I'm going to do is I'm going to discuss a procedure that, given a number theta, determines the values of cosine theta and sine theta, except that this procedure that I'm going to describe is something you can only do in your imagination. You can't really do it because it presumes having certain things lying around, like an ideal unit circle and an ideal piece of mathematical string that you can lay out to any length you like. So, of course, those things don't exist, but even though this is a procedure purely of the imagination, this will provide enough information about cosine and sine that will get you through Calculus 1. And I should mention that before we begin, that for a rigorous version, you have to wait till the end, pretty much, of Calculus 2. All right, so now let's begin. Consider the unit circle x squared plus y squared equals 1 in the xy plane, and here it is. Hopefully you remember how this goes. This point here is 1, 0, 0, 1, minus 1, 0, and 0, minus 1. All right, so given a number theta greater than or equal to 0, we'll get to negative theta later. If I want to find the values of cosine theta and sine theta, here's what I do. I start at x, y equals 1, 0, right here, and I take my ideal mathematical piece of string of length theta, and I measure it out along the ideal unit circle. Okay, so this is the part where it's just in your imagination, but still, I measure out a length of theta along the unit circle going counterclockwise, like so. So you can imagine I started off with a piece of string like this length, and I laid it tight along here, and I ended up here. And let x, y be the point where you stop. So here, x, y equals minus 0.8, 0.6. And if that's where you end up, then the idea is that cosine theta is equal to the x of where you end up, and sine theta equals the y of where you end up. So pop quiz, what's cosine theta and sine theta for this particular value of theta here? All right, that's right. It's cosine theta equals minus 0.8, and sine theta equals 0.6. All right, so that's your procedure. Oh yeah, I should mention what happens for theta less than 0. For theta less than 0, you do the same thing, except for the negative string, so to speak, is laid out clockwise instead of counterclockwise. So here, if we start off with a piece of string of this length here, except negatively, then I end up at minus 0.8, minus 0.6. Then what's cosine theta and sine theta? That's right, cosine theta equals minus 0.8, and sine theta equals minus 0.6. All right, so that leads to a couple of things going on here. I mean, so that seems kind of vaguely imaginary only, but it actually gives you lots of useful information. For example, since cosine theta, sine theta is a point on the unit circle, x squared plus y squared equals 1, well, cosine theta quantity squared plus sine theta quantity squared is equal to 1. That's the definition of what it means for this point to be satisfy this equation. Now, unfortunately, everybody has gotten used to using this abbreviation that cosine theta quantity squared is written cosine squared theta, and sine theta quantity squared is written as sine squared theta. Well, that's life. It's too late to change it now, so I guess it does make this identity a little easier to say, or at least more familiar. This is saying that cosine squared plus sine squared equals 1. All right. Oh, yeah. One other thing I should mention that comes out of the description that we just had, since laying out a length of string of length 2 pi gets you where you started, that means that if you lay out a length theta and then go around another 2 pi, you just might as well just laid out that length theta and not done anything else. In other words, the cosine of theta plus 2 pi is cosine theta, and the sine of theta plus 2 pi is equal to sine theta. The string procedure, adding on an extra 2 pi, is the same as the string procedure that you got by not laying out that extra 2 pi. In other words, if you think about what these equations mean, both cosine and sine are periodic with period 2 pi. Okay, so now I want to get some special values of cosine theta and sine theta in order to eventually construct a graph of cosine and sine. So let's make a table of some of these values. Let's see, how does the procedure go? Well, let's start with theta equals 0. For theta equals 0, we start off at 1, 0 and don't lay out any string at all, so we end up at 1, 0, which means that the cosine of 0 is 1, and the sine of 0 is 0. All right, so next up, we're going to have theta equals 2 pi. Well, the circle itself has circumference, or length, of 2 pi, so if I lay out a string of length 2 pi and go all the way around, boop, well, I'm just going to end up back where I started again, at 1, 0. So again, the cosine of 2 pi is 1, and the sine of 2 pi is 0. Okay, one more length before we go to another slide because I'm running out of room here. Well, if I lay out a length of a string of length pi, when starting from here, well, I'm going to go halfway around to 2 pi, which means I'm going to end up on the other end of the circle. And so having gone halfway around, we end up at -1, 0. So the cosine of pi is -1, and the sine of pi is 0. All right, moving to another slide just because we ran out of room. So here again is what we've figured out so far. Now for the next column, pi over 2, well, that's going to be halfway between 0 and pi. And so we're going to end up here at the top of the circle at 0, 1, which means that the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. And last bit of string to measure out, the length of 3 pi over 2. Well, here's 1 pi and here's 2 pi. So 3 pi over 2 is 1.5 pi. So I'm going to go all the way around here down to here, halfway between pi and 2 pi, and we're going to end up at 0, -1, which means that the cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is -1. Great. So what does that tell us? Well, now, if in principle, if you do this for every single value of pi, then you recover the graphs of cosine theta and sine theta as functions of pi. But even just with these 5 values, you can get a lot of information. So having done that, let's switch to the variable x instead of the variable theta. And we're just going to use these 5 values of x to try to sketch the graphs of cosine and sine just a little bit. Well, for the graph of cosine, we see that for the x values 0, pi over 2, pi, 3 pi over 2, and 2 pi, we have the corresponding cosine values of 1, 0, -1, 0, 1. I just copied that from the previous page. There it is. And so when I graph that, I get 1, 0, -1, 0, 1. Well, I got a graph that kind of looks like it goes down and it comes back up. Okay. Now, so for sine, similarly, I'm going to graph for those same x values. I'm going to get a graph 0, 1, 0, -1, 0. And so that's what the graph of sine x looks like very roughly. Again, between 0 and 2 pi, it goes up and it comes back down and it goes back to 0. Great. Okay, so that gives us very rough graphs of cosine and sine. So if we did this, in principle, if we did this for many, many more values of x, or all of them, then we get the sort of much more precise results, the sort of nice cosine and sine graphs that you're used to. And here they are. Here's the graph of sine for x between -2 pi and +2 pi. You see between 0 and 2 pi, we do the same thing as the blue graph from before. We go up, we come down, we come back to 0. And because sine is periodic with period 2 pi, we have the same thing happening between -2 pi and 0. And for the cosine of x, if you remember what we had before, we started up at 1, we go down to -1, we come back up to 1 between x equals 0 and x equals 2 pi. And so here we have that here, rounded off, because we put in a lot more values. And again, because cosine is periodic with period 2 pi, the same stuff happens between 2 pi, -2 pi, and 0 as happens between 0 and 2 pi. All right, turning to the other trig functions, there are four other trig functions, and they are best understood as being derived from sine and cosine for our purposes. So we can define the tangent of x to be the sine of x over the cosine of x, the cotangent of x to be the cosine of x over sine of x. The secant of x is defined to be 1 over cosine of x, and the cosecant of x is defined to be 1 over the sine of x. So those are just definitions for our purposes. And these functions are also periodic, but with period pi for tangent and cotangent, and period 2 pi for secant and cosecant. And here are their graphs, just for completeness. All right, like I was saying, tangent and cotangent each have period pi, and so here's one period of tangent. That goes going between -pi over 2 and +pi over 2. The graph goes up like this. I should mention that even though there are these vertical-looking lines here at +pi over 2 and -pi over 2, those aren't really there. They're kind of an artifact of the computer program, but they are actually sort of nice for indicating the fact there is in real life, well, in actuality, a vertical asymptote here and a vertical asymptote over here. And similarly, the graph of cotangent looks kind of similar, except that you get the asymptotes at 0 and pi and -pi instead of pi over 2 plus an integer multiple of pi, and instead of going up, they come down from 0 to pi, and from -pi to 0. All right, so that's the graph of cotangent. Again, a secant and cosecant x each have period 2 pi. And as we see here, actually, this is a tricky. If you ever have to graph secant or cosecant yourself, one neat trick for doing this. So here's the graph of secant here in the red, and here's, for comparison, the graph of cosine in green. And so the neat trick is one, at least sort of, if you want to get a qualitatively effective graph of secant, what you do is you draw the graph of cosine. So here's the graph of cosine between x equals negative 2 pi and x equals positive 2 pi. And what you do is you then flip it over. So you can, I mean, it's not really exactly flipped over mathematically, but at least in terms of a vague picture, it kind of looks like you just took these green hills and flipped them over to make them into valleys with sort of jumps, or actually again vertical asymptotes at pi over 2 plus multiples, integer multiples of pi. So again, if you ever have to, I don't know, if you're stuck in a dark alley or in a desert island and you're forced to graph secant x by hand, one convenient trick again is to graph cosine first and then flip it away from the x-axis. And in a very exactly analogous way, if you want to graph y equals cosecant of x, one way to do this is to graph sine of x. So here in green is the graph of sine of x, and then it's again flipped away from the x-axis, and you get asymptotes at multiples of pi. All right, that's enough for now. Thank you for your attention, and go do something useful. Goodbye.